Hi everyone, I'm Oriol Sánchez. I used to work in the Marine Science Institute in Barcelona, and our project was to develop sea ice monitoring buoys. We say buoy, but they are not actually buoys because they were designed to be put on top of the ice so they don't float. That's for the first thing I have to say. So a little bit of why we use that systems or what we were aiming to do there. So we were studying sea ice thickness and sea ice dynamics in the Arctic. And this is quite important because in the last 30 years, we have seen a very big trend of sea ice shrinking every year. And this is just an example, the minimum and the maximum of sea ice extension in 2016. And you can see also here. This is the median, so this is the average from all the records, and you can see that it's a pretty bad picture. Here you don't see it as a big bad picture because you see a lot of extension, but this ice is thinner than what used to be. So the thing is that you need to monitor this kind of environment, but you cannot be there because, you cannot be there. So you have to build either remote systems or in situ systems. And for that this isn't just an example, historical example. Back 100 years ago, you will just go with a ship with, for instance, the Fram. You can just get tethered in the ice and you just go and drift over for a year up to when you go to the other side of the Arctic. But then you have to put 20 persons in a boat for a year, and it's a bad idea. So you end developing automated systems. And just on a comparison of the science you can do with a ship 100 years ago and what you do with a buoy today. I will explain later why this buoy is like this. So we'll just come back later. But just to make you an idea, with this ship, they got 3 years of data, but the positioning, the data, the resolution of the data they got, it was like 1 degree, and so 1,800 meters. And with these systems, we were getting centimeter level positioning data in the 3 axes. So that's quite amazing for those systems. It's okay. It's very expensive. So why don't you do it with satellites? So the big problem is that there are satellites doing that, but you are not measuring in situ data. So what you are measuring is the difference between the pulse of a radar beaming to the top of the sea ice and the pulse beaming into the water. So you are measuring this distance. The problem is when you go far from the shore of the sea ice, your reading is false. So the far you go from the shore, the worse is your reading. So what you have to do is to complement those systems with our systems. So it's kind of a cycle. We calibrate those satellites with those systems. So there has been an evolution since the start of the project. We started in 2010, and initially it was a project done by CSIC and the Scottish Association for Marine Sciences, and we were doing this together. At some point, the scientists in charge of these projects, they just split up, and we continued doing our system, and the other guys drifted towards other projects. British Antarctic Survey, Alfred Wegener Institute, and University Pierre Marie Curie of Paris. And this thing of here, the MIT, is because the lead scientist in the project, he left also the project to go to the Haystack Observatory of MIT. But with all this picture, what I want to say is that from this start, a lot of the work that was done here has been reutilized in our system mainly, but also in all the other systems that are working nowadays in the Arctic. So this is the system. What it records is positions in the 3 axes at centimeter level precision, and we get snow thickness, we get conductivity and temperature of the seawater, and we have a weather station with wind and atmospheric pressure and so on. And we have a camera that is only used for engineering reasons to see whether the buoy is still in one piece or not. And the other aiming of this camera was to see whether there were many melt ponds on the surface of the ice. We can go back to the melt ponds at the end of the talk if you want, but it's a complicated issue related to how you model this information into the cryosphere model. So this, as I was introducing, this system is used for marine geodesy, sea ice mechanics and dynamics. If you have a matrix of 3 buoys, you can see the formations of the freeboard of the sea ice. We can use those data also to calibrate satellite altimeters and validation of sea ice products from other kinds of satellites. There's another satellite being operated by ESA, but by the European Space Agency, but the process center is in Barcelona also, where Nuria works, in the Marine Institute of the Institute of Marine Sciences. This is the ESMO satellite. It is a different kind of sensor, but they recently discovered that, I mean, the main use of that satellite was to get moisture from land and salinity from the water. But they realized that when their satellite was recording data in regions where there are supposed to be sea ice, that they could infer the data, the thickness of the ice when that ice was thin enough. So that complements the other kind of satellites where you were deriving the data from the difference of height, and you need the ice to be thick. And in between is still our system. So this is our computer inside the system. It's an Italian microprocessor unit. It's an Acme Systems. The thing on this system is that it's what connects all the other projects in the European Union with us. I mean, almost all the people is using the same microprocessor unit on their systems, and it's just like a Raspberry Pi. But overall, I mean, you can go with different embedded solutions with real-time operation systems, Windows embedded, whatever you want. But in our environment, it's much more easier to just go with Linux. I mean, and Linux embedded. And I mean, that's the point. And this is the PCB, the motherboard of the system. What is, I mean, this is our main sensor, the GPS, the receiver. But what you can see in this PCB is that it is designed with solid state relays over here, here, and here to try to minimize all the consumption of the non-essential parts of the PCB during winter, because when you have your system in winter there, you don't have sunlight, so you cannot recharge batteries. So you have to try to get the data out without any energy more than your batteries that you already have there. That's important. We will see that later. Why? I mean, this is the block design of the system. There's the CPU with some of the sensors, the GPS, the modem, the data modem, and this is a data logger. This is a commercial data logger for oceanographic sensors, for the conductivity and temperature of water in the sea. We use those kind of sensors because it's a working solution. So this is the code of the system. It's quite easy actually. The Campbell, the data logger, the proprietary data logger, uses their own version of code based on BASIC. But the Fox board, the CPU, it just runs Debian kernel. And on top of that, we just run through init, so initializing on the boot, or through cron tab, just launching the scripts through the cron. Several different scripts written mostly on Python to do several stuff. I mean, comes after that. So wasn't this about Python? Yes, this is about Python, and we use Python for a lot of things on that project, from data acquisition up to visualization. And we'll just go quite quickly about all of them. But you have to understand that in science, the teams we have for developing all this sort of stuff are not quite big, and we don't have really a lot of resources to do this. So we try to get a code that is reusable and that can be integrated in many different systems. So that's why we just drifted naturally towards Python. The first thing we use it for, data acquisition. We have on the embedded computer, we can reach I2C bus and serial ports. And what we try to do here is to write general drivers, so you can just get all the work you have done in this system and put it into, for instance, UAV if sorts. So UAV, an underwater autonomous vehicle. AUV. So well, anyway, what we were doing with this is serial port, TTL, and I2C ports, and then the main system that it was the GPS receiver. We were reading the entire observations of the GPS. With this, what you are building is a Renex file. We don't get positions. What we get is the information of the delays of the signal from the constellation of satellites, and then we post-process this data in Barcelona. And this is done because if you want to get up to the centimeter level precision, you must get the raw observations from your system, get them into your server, and 2 weeks after those are read, the NASA gets you the information about the ionospheric weather and the orbits of the satellites. So with this information, you can reapply the GPS equation, resolution equation, and you can get to the centimeter level position. So the weather there is shitty, it's very shitty. So any kind of sensor you have there is going to go through, I think it can be one of the worst environments you can find. Because I mean, even in space, the heat you generate normally, you only radiate the energy, but you really don't have convection or conduction. In the Arctic, any kind of heat you generate is going to fade away. So you also don't have a lot of extra energy to burn into heating your system. So some of the systems we have there are really useful only in summer. So, but I mean, this is a general issue. Everyone knows about that, but you have to work with whatever you have. So this is the code for the sensors. As I was explaining, we have a specific Python scripts to read the GPS data. And we have the specific code for building. It's very simple. You get the data from the sensor and you build a CSV table. And we also have code to read the raw data from the sensors on the PCB. And this is one of the last improvements we did. We realized that we were taking 4 photos a day, and that doesn't make sense if you want to see the status of the buoy and to see if there are meltpoints around the CA surface. So what we did was to use the information we had from the GPS to calculate the first approximation, first position. From that we get the latitude. from the latitude, we can estimate the sunrise and the nighttime, and we just time the two photos to one to be on the dawn and the other one to be on the end of the day. And with that, we are saving two photos. It's not a lot of data, but we are saving energy and we are saving bandwidth. And every byte and every byte counts there. So the communications, I mean, it's kind of silly, but I mean, that's generally how you work with this kind of network. What you are doing is just scheduling an hourly call to the satellite network, where you will try to see if there are available satellites over you. If there are satellites, you transmit your data, and if there are no satellites, you just cut down the energy because you are wasting energy. So this is the network we were using. It is the Iridium network. I don't know if anyone of here knows about that network. I don't see. Yeah. So 2%. Yeah, that's good. So this network, the particular thing is that it's the only satellite network that has complete global coverage, so from pole to pole. But it's a network that was deployed in the early 90s. So your bandwidth there is like, it's stupid. I mean, it's like 2,000 bytes per second, which in nowadays it makes no sense. So bits per second. Yeah, bits per second. So anyway, the thing is that this network was designed originally to do voice calls. So you have to adapt yourself to try to get whatever you can from this network. And it's protocol-less. It's originally was point-to-point protocol, and it was falling apart, the constellation. Nowadays, they are relaunching a new constellation of satellites. But when we were deploying our systems, that constellation was not there yet. So what that means is that your link to your base station, it's going to fail a lot. I mean, you cannot pass a lot of data, and you don't have, you have the TCP stack if you work with PPP, but in 2015, they abandoned PPP because of performance problems. So we had to move forward, and in the third generation of buoys, implement a new system that is called Rudix. What Rudix is, that is just substituting your base station that is working with the Iridium network. So originally you are calling from the remote system through the Iridium network to your base station, straight, that line. And you build a TCP stack on between of those two systems. Nowadays, what you have is a gateway in between. So you are calling your system through a gateway in Colorado, who is then beaming the connection through the network. That adds another step on the communications algorithm, and what it does is that it's essentially getting you more doors between your buoy and your server. What this means also is that you don't have a protocol now. You can try to implement a protocol, but because of the low speed and the low performance, you are going to waste a lot of bytes doing that. So what you have to do is to build your own protocol. And that's one of the things we were doing. This is the original system where you had your ground station and your remote system. This is the TCP, the OSI layer setup. And I mean, you have your own scripts that you just build on creating a TCP, a PPP connection between them. The new system, the Rudix, forced us to forget about this and go into this scenario. And with this scenario, we were implementing the system with Python. Now we are building a system where we just transmit the data in binary format with checksum code and the usual stuff you would find in a normal TCP stack. But we're just doing it raw. I mean, without any other support rather than our scripts. So long the system, the algorithm was this one. And by time constraints, and mainly because I was the only engineer in the project in Barcelona, we got up to this. Time was going, and the project had to be finished last year. So we just called one of the friends we had from the start of the talk that are using our same system, and we just use their program for communications. So anyway, I will put this all this code in my GitHub if anyone has interest on this, and we can figure out the last part if you want. So this is all this code that I was talking about. This is mainly a script to operate the Iridium modems. This script was doing SVD messaging, PPP FTP protocol that is no longer supported by the network, raw ASCII connection, just so you can just send text, and the Rudix algorithm. Then we have a wrapper with pandas to do CSV stacks and lists, a wrapper to do Linux, to run Linux commands, and a wrapper to, a big problem that just imports all these scripts to do the communications on the buoy. And then we have the final part, the server, that uses some of those scripts also to finish the algorithm. And those are the systems that were deployed in the project around here. And this one was deployed in 2012, and this one in 2013. Those two in this one and this one was in 15. This one was also in 15 by another ship. And those four were deployed last year by me. Yeah. So this is the data visualization we were using at the start of the project. We were just using matplotlib to plot static graphics of the data we were obtaining from the buoy. And we implemented just matplotlib, plotly. So what we were adding is a dynamic front end for the website. I don't have Wi-Fi, so I cannot show it you, but this is also still working on the server in CSIC. Moving on, this is the deployment, the last year's deployment. Sorry. So what I was going to say is we were deploying this system with 2 persons, and the third person is the most important person in the field, really, because the other person is the bergward. So is the one that is making sure that nothing is going to eat you. The system, what you see here is just the tip of the system. This here is the batteries and the solar panels. And what we have to do is a hole through the ice, 2 meters thick ice. And down into the bottom, you have the sea level sensors and this conductivity and the pressure sensors. Sometimes you have to deploy the systems far from the ship. So that means you have to deploy them with helicopter. There's another story I will just tell you about when this finishes. So yeah. So another important thing to realize, you see the horizon here? you see it because you see water. But when you are flying over the sea ice and you have a reference, a water reference, you think you could see that horizon. So neither did the pilots on the helicopters. So that's sometimes tricky. And also there's another phenomena there. When you have mist here, it's not a big problem. But when you have mist in the Arctic and you are flying with an helicopter, that mist, if you are under 0 degrees, is going to build up on the helix of the helicopter. So you are going to lose lift on the helicopter and it will just go down. So that happened to us the second day of deployments, and we were stuck into the ground for 5 hours. Luckily for me, at that time, we were deploying one system 300 meters from the boat, but our partners, our French partners, were deploying a different buoy 5 kilometers from the boat. That was a really scary moment, because at some point we had to decide if we could combine the helicopter pilots to go there flying low with the risk of crashing, or just to abandon the big float where we were stationed with the ship and go to rescue those guys. Everything went fine and we just went with helicopters, but at that point we were flying like 15 to 20 meters from the ground, and I can tell you that this is scary. It's pretty scary. But anyway, all the systems were deployed, and the French system was also deployed. Nobody was hurt, and we were getting data from there, so everything was fine. Yes. So those are the systems we deployed here. These are satice system. As I was telling, uses 2 power units with solar panels, and those batteries are designed to provide power for the winter. And this is the French system. He's one of the French guys that was stood there for like half a day. But that's another story. 2 years ago, coming back to the start of the talk, we introduced that we were developing the systems at the start with the Scottish scientists, who at the end went to the British Antarctic Survey. This is one of those scientists, and they have their own buoys now that measure different stuff. This one is measuring wave dynamics on top of the sea ice, and this one is measuring thickness with a thermal chain. Our system did measure also thickness, but we were using water pressure on the bottom of the water, and a fixed reference on the top of the ice to derive the thickness from real distances. And what they are using is a thermal chain with sensors spaced at 2 centimeters to look at the interface of the mediums, air, ice, and water, where the temperature gets dissipated at a different rate. So that's how they measure the thickness. So anyway, this system is installed with a through-hole bore into the sea ice, and this one, it has a suitcase and then a small hole with a sensor on the bottom. The thing is that when we installed those 2 systems, we were like 15 kilometers from the boat. We get there by helicopter. We deploy the systems. One of the pilots was kind enough to bring us dinner. We ate one of the best burgers I ever had, and we left with the system working. So it was really fun, really amazing, and so on. The problem was that 2 days later, this guy was turned around by something. So luckily, they had it's not mounted here, but they had a camera here. So it's when you try to get the suitcase the other way around, it will be tilted at like 45 degrees. This is important because they also use the same EDM network that we use. So they could get in-node coverage to get some data out. And we got the photograph of the system turned upside down. So it was a polymer. So the lesson here is just don't eat around the buoys when you deploy systems. The satice, the satice system I was talking about at the start, is SI04. It was deployed in 2012, and the interesting thing about this buoy, I'm going back a little bit. Yes, so this buoy was deployed here and drifted for almost 4 years around the North Pole, giving data back. It was a record for us. And this is when we got a position, the last position from the system in 2015, and we told that to an icebreaker. And they got to change the route to their course to see if that system was really there. And this is what they found. And that brings us to one of the first things why I was telling about. This system was deployed, was designed to be installed in multi-year CIs. That is no longer the norm there. Because as I was introducing, the CIs is shrinking and it's getting thinner every year. So luckily it was still getting data out, but the newest scenario with the AIs calls for a redesign of the system. So redesign the system. So new PCB, new data protocol, new CPU, because the ACME board we were talking about, it has been upgraded by the manufacturer also. We need a new wind sensor that doesn't get frozen, and so on and so on. And the most important thing, you have to make it float, because that's the newest scenario in there. So that's the last proposal I made to the institute. It was just embedded everything into a system. So it would go with the batteries inside here. And also adding this system here, because one of the things we noticed happened 3 times, is that once you get your melting season, there start to open leads among the cells. So that means that your floats are no longer fixed, but they are sailing and colliding between them. So if you are unlucky, what it could happen is that you have your buoy here, like this, and then you have 2 CIS floats going close to one to the other, and then one goes up the other, and just the other one slides in and just breaks the lower part, the lower section of the buoy. So what we suggested is just to build a system to purposely break that part, if that happens, and still keep the buoy to keep working and providing data. That's the last thing we were proposing, and that project, that's the biggest limitation we had in the project. We were 1 engineer at the time working on the project. That project ended, and you can still get information from it from my campaign log here, or from the project here, project website, where the plots are and the maps of the systems are and the data is. And this ended this year, and I'm moving forward to another weird project of embedded electronics in the sea also. And this is what we are doing nowadays. I'm in a small company. We are building rigid sails for all ships, all kinds of ships. And I'm trying to bring my love for Python into the system too. So I'm trying to put embedded systems for acquiring data on the system, on the control on the ship. I'm trying to get my simulator crew to operate hydrodynamic and aerodynamic simulations with Python scripts. And we have to build a server, which I intend it to be as most Pythonic as possible. And well, that's all for today. If anyone has a question or just go.
No questions? No questions. So what is approximately the cost to construct the system?
Yeah.
How much of engineering?
So this is on the start. So, as cost for today, I mean, building a ship, this is cheap. I mean, in nowadays terms. Operating an icebreaker for one day, it could be something like 100,000 euros. And building one of our buoys is like 20,000 euros. But the difference is the ship has to return to harbor, and our buoy can be there for like 4 years if we are lucky. So the really economic cost you have to see there is the price per byte of data we get.
And in the case that another sea ice was breaking the down part of the system, that system was no longer used?
It is still used for dynamics, but not for ice thickness. Because the ice thickness is derived from the sensor you have on the bottom. But with the data, with the reference you have on the surface, you can still do a sea ice deflection.
Mm-hmm. And you said that the sea ice is becoming thinner and thinner.
Thinner every day, yeah.
That's the result. But in the best case scenario, what is the lifetime of that system? Is it up to 4 years? Or?
Yeah. Technically, the Arctic, I didn't talk about currents. But there are two main water currents in the Arctic. So you have the transpolar current that connects the Bering Strait to the Atlantic through the coast of Siberia. And then you have the B4 gyre, that is a circular current here. That is our area of interest, because what it's going to do is going to contain sea ice on the area for more time. So that is where you find the multi-year sea ice. That sea ice is the one that is being shrinking more rapidly for the last 20 years. It's a struggle because originally you have a lot of interest of scientists, glaciologists, and cryospheric scientists to trying to study the area to then bring more understanding on the global climate model. And then you also have a lot of interest of drilling companies, transport companies, shipping companies that are just expecting the sea ice to entirely go in summer in 2015. Entirely in summer. So we still have. Yeah.
So, first, I was curious about what kind of energy harvesting mechanisms do you have? What kind of energy harvesting mechanisms do you have? Because we're talking about PV cells.
Oh, the performance of the PV cells.
If you had any other type of energy harvesting.
Oh, yeah. At some point, the Scottish were testing a system to harvest energy from Seebeck effect. So that's you have a big tube with heating transport tube, the same kind of tubes you have in a laptop to transport the heat from the CPU to the fans outside the board. And what they were doing is to harvest the energy from the difference of temperature between the water and the air. And they got to a working prototype of 3 meters long and something like this thick. And they were harvesting half an amp, 5 volts with that system. So yeah, it's more than nothing, but it's not the perfect solution. And then there's always the Russians. But this is another thing they do. The Russians in the Arctic, they had radio stations, radio lighthouses for shipping, and they were nuclear powered. But I mean, this is a kind of different beast. Technically, you can go with something similar you have in the Mars rover in a system for a remote area, but you don't want that to be in the water. Maybe if you were studying glaciers in Greenland or inland. So yeah. Can you just?
If the components are commercial, or you are doing your own?
The oceanographic sensors, they are commercial. Because we need them to be as realistic, the data, as good as possible. But in some cases, for the engineering sensors, we call engineering sensors the temperature of the PCB, humidity inside the system, or these kind of sensors. They are just sensors from PCB sensor. I mean, RS components or Farnell, this kind of shops. Test them and validate in-house. Yeah.
In this kind of project, it is so important to test everything, I guess, because if something breaks there, you cannot go there. So and you cannot afford to break your computer. How do you test everything in these conditions? Because it seems to me that this is so much. There's lots of lots of things that can go wrong.
Yeah.
And also the communication, it's also handled by your scripts, and you have to validate them. And did you have to update anything over this slow communication?
Yes. So one of the big rules is you don't update anything after you have got your system out from the lab. So as it gets out, it's the way the software is going to remain. And before it goes out, we do a burning test of all the systems in our laboratory for 2 weeks to validate that everything is going to work. But obviously, we cannot simulate neither the temperatures nor the humidity. So it's not a perfect test.
More questions? Last question. More questions during the beer
and pizza, and pineapple pizza.
Yeah, because we have Gabi that is going to explain about Dataton is going to be empty this year.
So you are simulating these conditions in the lab. So did you lose any buoys to like environmental things apart from the polar bear?
Polar bear is an issue, big issue, but mostly, as I was talking, the situation in the Arctic has become much more active in the recent years. So that means that you have sea ice floats ringing against each other. And we already saw 3 systems getting bended because we suddenly got to see spikes on the distance between the sea level from where we were recording. So, for instance, when you see that your sea level is located at 3 meters, and suddenly in the next set of data, 15 minutes later, that sea level is now 2 meters up, then you know that your sensor has been bended and that you are just reading a false reading. And that happened for 3 systems at least. And then in some other systems, you try to locate the best float possible, the more thick float you can, but you are not driving the boat. So you have to make the best thing, to have to find the best spot you can. But what happened to us is that in the last campaign, we found ice that was generally between 1.5 to 1.7 meters deep. That's quite thin. And when we found spots where the thickness was like 2-3 meters, we knew that those spots were not really one block of ice, but one with the other down. So that means that the survivability of the system there, it's probably around 2 months, 3 months. The good thing is that when you get to survive up to the start of the freezing season, you are most entirely sure that you are going to do it over the winter, because everything gets colder.
So it's more dynamics than
Yeah, much more.